point the camera of your phone at that link, and it should offer to take you to a website. So I'm just going to leave it up there for a minute. And oh, good. If you point your camera at the QR code, it should recognize it as such and ask if you can take it to a website, and it should do that. Okay, well, I'm going to try now to see if I can go to the next slide without creating anything too crazy. So a little bit of an outline, and I think probably sea kayakers are the group that is most affected by tides and tidal currents, because we're relatively slow moving vessels, and so any kind of tidal current can really slow us down or speed us up. And so I'll talk a little bit about the patterns, how they work, and then talk about a few resources at the end. And this is a picture of one of our intertidal paddles with Dave Giuliani in the back there in the canoe and me in the foreground on a nice sunny summer day on a low tide. So first of all, tide heights. There's a lot of places that have incredibly high tides. This is Anchorage, Alaska, and you can see that the tide gauge there goes up to almost 50 feet. And another famous spot in the Bay of Fundy, some of you may have gone to Hopewell Cape, and there the tides can be as much as 16 meters, which is over 50 feet. And basically, you know, some places have incredibly big tides, other places have some smaller tides. And here's a list of the top 7. And you'll notice that the top 2 are in Canada. So we have a little bit of a claim to fame there at 12.9 and 12.5 meters. And the others are spread around the world. But there's some pretty big tides out there. So when we look at tides, you observe a lot of changing patterns, and the basic pattern takes 24 hours and 50 minutes, and we call that a tidal day. And the bottom paragraph on the screen is sort of a definition of a tide, a distortion in the shape of one body introduced by a gravitational pull of another nearby object. And basically all objects experience tides. The solid rocks of the earth experience tides. We technically experience tides, but the amount and the effects of those forces are minuscule on some of those scales. And because rocks are not very stretchy, they don't move very much, but they do actually react to tides or tidal forces. So the first question is, why is it 24 hours and 50 minutes? And the first thing is, most people think that it takes the Earth 24 hours to spin on its axis, but it actually takes 23 hours and 56 minutes to do that. But what is the Earth doing every day? It's actually revolving around the sun. And so in one day, it's revolved 1/365th or so of a circle. And so once the Earth is spun around once, it has to spin around a bit more to point back at the sun. And that's why the spin time is 23 hours and 56 minutes, but the daytime, which is noon till noon, is 24 hours. So hopefully that sort of makes sense. So the Earth has to spin, and then because the Earth is orbiting around the sun, it has to catch up a little bit to get the sun at the same point in the sky. So similarly, the moon orbits the Earth in about just over 27 days. And that's the time but the time that each spot, so if you imagine the moon is above you on one day, and you want to spin round and have the moon above you the next day, that will take 24 hours and 50 minutes, because while the Earth is spinning, the moon is also orbiting the Earth. And so you have to catch up. And so that's why there's this thing that we probably all noticed, is that if you go to a beach one day and you notice that, you know, high tide is at such and such a time, the next day, the same high tide will be about 50 minutes later. And sorry, no, not the next one, but the next day's high tide, because we generally in most places have two tides per day. And again, that's another complicated story. What I thought I would do first of all here is just show you a few diagrams or plots of tidal patterns. And I've given you Oak Bay at the top left and Port Renfrew at the top right. And these are both for the same day, which I think, did I put the day on there? It was about a week ago when I was putting this together. So it was, but basically you'll notice that the Port Renfrew pattern is a bit more, I say properly sinusoidal, but it's still quite mixed. Whereas Oak Bay has virtually, you know, the entire day is a high tide, and more on that later. Down below, I've got, again, for Oak Bay and for Port Renfrew, I think I've got 7 days graphed there. And you'll notice that the shape of the graph changes each day, but you'll also notice that over those 7 days, the range of tide gets less and less over that time. Does that make sense? So you can see that the first day's range goes from, in the case of Oak Bay, from about 0.5 of a meter, sorry, 0.5 of a foot to a little over 10 feet. Whereas on the last day, it's almost half that length, half that range. So when we're looking at these patterns, we want to figure out, you know, why is it different in one place than another? And also, why does it change how big it is from one day to the next? And something else you might notice on the top 2 graphs is that the very, the time, sorry, the red line there is about the same time. It was like a minute different for both of those graphs, but the high tide in Port Renfrew was earlier than in Oak Bay. And that kind of makes sense because the tide has to actually flood through the Strait of Juan de Fuca and onwards. So I found a really good website that's in the resources later. And this is based, this shows you kind of the patterns for Seattle, which is actually quite similar in a lot of ways to Victoria. And you'll notice that, you know, the first graph just shows you 1 day, and then the next graph shows you 1 month. And I think that 1 month graph is pretty neat because you can really see how in the first like quarter of the month on that graph, there's some really big tides. And then about a third of the way in, there's some pretty small range tides. And then again, bigger tides, and then again, smaller tides. And so that's 1 month. But then the bottom graph there shows you a whole year. And you can see that there are a few more patterns to the overall pattern than you get just in a month. And you'll see that there are certain times of year when the tides are much bigger overall, or I should say the big tides are bigger, and the other times when they're smaller. So just showing you a few more graphs. This is Oak Bay in, I think this was in December. And yeah, this is December. And you can just see, again, kind of this sort of daytime high tide with 2 very unequal tides. And then here's Oak Bay again another time. You'll notice that the previous one, you had the small tide first and the big tide second, and then here the big tide first and then the small one second. And the second tide is basically almost non-existent. And if you look at the third day on that graph, you can see that there's really one high tide and one low tide in the day, because the second tide is almost kind of wiped out. And again, just another example of Oak Bay. So you can see that the patterns here, especially in the winter, are pretty weird for Oak Bay. And we have some of the strangest tides around Victoria, strangest tide patterns. Whereas if I go to Banfield at the same time, it has a much, much more regular pattern. And you can see here, it's a very much sinusoidal pattern, and where the two lows are kind of the same height and the two highs are kind of the same height, though not exactly. So things that we want to try and explain are, why do the tides have bigger ranges sometimes, and why do they have lower ranges? And also, why do we have two tides in one day? And then another thing we want to try and explain is, why is one of the peaks a different height from the other peak in the same day? So those are kind of three things that I would like to try and address. So the first question is, does the tide go up and down? Well, it sort of appears to do that, but what's really happening is that the Earth is rotating through tidal bulges. And if you imagine that there is a bulge of water on the two sides of the Earth, one pointing towards the moon, one pointing away from the moon, and the Earth is spinning through those bulges. And so the bulges are more or less staying in the same place relative to the moon, and the Earth is spinning through them. And so my related question is, does the sun actually set? It depends on your perspective. So going back to those patterns, there are three general kind of tide patterns that have been classified. The two more or less even tides a day, we call that semi-diurnal. And then other locations have just one tidal cycle a day, and that's called a diurnal tide. And in many places, the tide are somewhere in between those, so we call that mixed. Now, if you go to Banfield, the tides in Banfield are typically, they range from semi-diurnal to mixed. And then in Victoria, they range from mixed to diurnal. And so it's, in one location, you may have more than one type of pattern. And so here we go. Again, this is Banfield, and Banfield on just a one-day view of Banfield. And this was in November. I guess I must have done this talk 2 years ago, because this was 3 years ago. This was 2018. And then if I go to the next graph, this is Banfield over a period of a week. And again, you can see going from small range tides to big range tides. And then again, just for kind of driving the point home, this is where you can see Victoria's tides are just downright weird. There's a book on British Columbia oceanography that has this diagram in it, and it shows you a month's patterns, and these were all in June of '77. And it shows you the tide patterns in 5 different locations along the BC coast. And you can see Prince Rupert has pretty what I would call normal tides that are kind of semi-diurnal to mixed. Same for Alert Bay. Point Atkinson is a little bit weird. Victoria is downright weird. And Tofino is almost normal, but it's still got quite a bit of variation there. And you'll notice that at the bottom end of that diagram, there are a few things noted. They've got full moon, new moon, and then full moon. That's the white circle, the black circle, and then the white circle. And you've got the two quarter moons. And you've also got some other things that are mentioned there. So can you see on in the very bottom left corner, it says P, and that means the moon is at perigee, meaning that the moon is closest to the Earth. In the middle of the diagram, just below where it says June, you can see an A, and that is apogee, and that means the moon is furthest from the Earth. You'll also see that it has an S, E, N, and then E, and then S, and that's basically saying, is the moon north of the equator, south of the equator, or on the equator? And more on that later. So those are kind of three things that the moon does that affects the tides. And it's important to realize that this 1 month here is just one example of a pattern, and the patterns change from year to year, and they kind of more or less repeat about every 18.5 years, but they don't completely repeat. Okay, so here I think, I'm hoping will work. Yeah, so this is hopefully a thing showing you kind of how the tide patterns change in Seattle over a month. And I'll just play that again. You can see the tide's getting bigger, getting smaller, getting bigger again, and then getting smaller again. So that's just the, and you can see the shape of the tide graph changes over that time. And the times of the high tides move forward 50 minutes every day. So where in the world do we get certain kinds of tides? And this diagram here shows you where the tides are typically semi-diurnal, which is the red lines, the yellow diurnal, and the blue are the mixed ones. So the semi-diurnal tides, you can see here, this is sort of a tide graph for a semi-diurnal. You can see the two highs and the two lows are pretty much at the same point. And then there's a few places in the world where we get diurnal tides, basically one high and one low each tidal day. And quite a number of places where you get these mixed tides. And most of the area that we are in is basically in the regime of what I would call mixed tides, where we get a high, a low, sorry, a higher high, a lower high, a higher low, and a lower low, which is some pretty confusing terminology. So those are the terms: higher high, higher low, lower high, lower low. And when you're reading the measurements, they are measured from a thing called datum, which is basically a benchmark point. And it's usually from a mean low tide. Now, the definition that is used in Canada and the one that's used in the US are slightly different. In Canada, they use a lower point. I think the average of the lowest low tides, whereas the US uses just an average low tide, which means that if you're looking at American tide tables, it's much more frequent that you'll get negative tides. I don't know if you've looked at Canadian tide tables, but it's very, very rare to get negative tides in Canada. But in the US, it's quite common. In fact, almost half of the month you get negative tides in the US. So we want to try and explain why the tide range is greater on some days than others, and that coincides with the phases of the moon. Actually, if I go back to, I'm just going to quickly go back to this diagram, I think you can see fairly clearly that the big range tides are right after the full moon, right after the new moon, and right after the full moon. And the smaller range tides are just after the quarter moons or the half moons. So I'm just going to go back to here. And we also see that that inequality, the difference between the higher high and the lower high, that changes over time. And there are a few other patterns that we'll also delve into. So there's actually some debate over how to explain this in physics terms, but I found that this is probably the easiest one to understand. The fundamental force that's involved is the gravitational attraction of the moon. And gravity depends on two key factors. One is the masses involved, and the other one is their distance. The bigger the masses, the bigger the force. And in the case of the distance, the smaller the distance, the bigger the force is. So that means that when the moon is closer, it's having a bigger effect. And when the moon is further, it's having a smaller effect. Now, the other thing that's kind of hard to understand with tides is that the moon doesn't directly orbit the Earth. The moon and the Earth spin around a common center. So how's that for being weird? So what I want you to imagine is if you had two equal size ice skaters spinning around each other on ice, they would spin around where their hands were together. Does that make sense? Norm, you can give me a thumbs up if that makes sense.
Yep, makes sense.
And the other thing is that if you have one of these ice skaters was 3 or 4 times the size of the other ice skater, where would they spin around? They would spin around probably the shoulder of the bigger ice skater. Does that kind of make sense? Because they're spinning around the common center of mass. And so the Earth and the moon are spinning around this common center, and you end up with essentially this sort of dance that the Earth and the moon are doing around this common point. And you get essentially 2 sets of forces, and those 2 forces work against each, or in some cases work against each other, and create 2 bulges. And so the tide on the near side, we call that the direct tide, and the one on the far side is called the indirect tide. And I'm just going to spend a few slides trying to show that. So here you can kind of see a diagram. I don't know if you can see on the screen, there's a little black and white kind of little disc that's on the edge of the Earth on the diagram there.
Yep.
And that is the common geocenter. And you can see it's sort of on the point. It's on the side of the Earth near to the moon. And that's the point around which the Earth-Moon system is spinning. So that's why you get this weird kind of dance of the Earth and the moon. So when we start looking at the forces involved here, you can basically look at what are the forces involved. And so you've got the what's called the acceleration, and F equals ma, force equals mass times acceleration. In a perfectly circular system, then the forces will always be balanced. But because you've got 2 like solid objects, you'll find that the gravitational force due to the moon is more on the moon side than it is on the opposite side. But the spinning force, the acceleration force, is the same throughout. And so I don't know if you can see on the top right diagram, there's these arrows here where you've got the green arrow, which represents the gravity. The brown arrow represents the acceleration force, or the net acceleration or centripetal acceleration. And can you see that all of those brown arrows are the same size because all parts of the Earth are accelerating at the same speed? And if you take those two forces and add them up, you end up with the little black arrows. And can you see that the black arrow points towards the moon on the near side and it points away from the moon on the far side, because those two forces add up to point in opposite directions. And so the bottom diagram is kind of summarizing that. And what I really want to kind of drive home is that if you have a distant attracting mass, namely the moon, off to one side, you're going to get these what are called tractive forces on both sides of the Earth. A set of forces pointing towards and a set pointing away. Okay, if you don't get that, don't worry. The key thing to realize is there is, in most cases, two bulges, one on the near side, one on the far side. Here's another diagram from the BC Oceanography book. And again, it's sort of showing you how the force of gravity, the centripetal force, and the resultant force give you a bulge on either side, because they kind of, on the one side they add together and the other side they subtract. So the other thing to remember is that the sun is very, very far away. Gravity forces, as you go further away, get less, but the sun is also very, very big. And it turns out that the sun's effect is 46% of the moon's effect. What that means is that when we're looking at tidal forces, it's really 2/3 moon, 1/3 sun. So that's an important thing to remember. So 2/3 of the effect is due to the moon. The other part, the other third, is due to the sun. And I think one of the easiest things to understand with tides is that when the sun and the moon are working together, which happens at the full and the new moon phases, we have spring tides. And by the way, spring tides have nothing to do with spring. They have to do with the German word sprungen, which means to leap. And then when the sun and moon oppose each other at the quarter moon phases, we have these neap tides. And I've got some diagrams here. So here for spring tides, you've got the sun and the moon working in the same plane, essentially, in the same direction. They add together, you get big range tides. And when they're working kind of against each other, you get smaller range tides. And then this, I think, I'm hoping will kind of, I don't know if you can see the shape of the bulge changing as the moon goes around the Earth. So we have neap tides, spring tides, neap tides, spring tides. And again, that's, I think, getting this idea that when the sun, earth, and moon are in a line, all the forces are in the same direction and they work together, and the sun and the moon add. But when they are at right angles to each other, they're working against each other. So here is a view of the year's graph for Seattle. And the kind of orange background is the overall shape of the tide pattern for Seattle. And then you've got the brown circles and the orange circles. And basically they're showing you the resultant forces at new moon and full moon. And those are going to be basically giving us our 2 spring tides each month and 2 neap tides. And you might ask, why are some of them bigger than the others? And again, that's to do with where is the sun, or what is the angle of the moon to the sun? And I'll come back to that one later. But you can see that basically the peaks, the big range tides correspond with either new moons or full moons. So the other thing to think about is both the moon's orbit around the Earth and the Earth's orbit around the sun are not circles, they're elliptical. And when things are closer, they have a greater force. When they're further, they get a smaller force. And that causes even more variation in the tidal pattern. And if you look at the moon's distance, it ranges from 357,000 kilometers up to 407,000 kilometers. So a difference of 50,000 kilometers in 400. It's about 12% or so. So it's a pretty significant difference in distance between the Earth and the moon, and therefore a big variation in the force that the moon's gravity will generate. And here you can see, again, sort of showing you rather exaggerated ellipse. But the other thing to realize is that the Earth's orbit around the sun is also an ellipse, and it ranges from, I'm sorry, I don't have this in kilometers, it's about 150 million kilometers roughly, but it's ranges from 91.5 million miles to 94.5 million miles. And that's about a 3 million mile difference, which amounts to about a 3% difference. So you can see that there's a significant difference or significant change between when the Earth is closest to the sun, which is in January, and when it's furthest from the sun in July. Okay. So the other weird thing is that the moon's orbit is tilted at about 5 degrees to the Earth's orbit around the sun. And what that means is that sometimes the moon is north of the equator, and other times it's south of the equator. And what that does is it makes the bulge lopsided. And if I show you this diagram here, you can see the dashed line is showing you the moon, and the bulges, obviously not to scale, when the moon is directly over the equator. And then when it's at high declination, you get this lopsided bulge, where one bulge is on the northern hemisphere and the other bulge is on the southern hemisphere. And that basically helps to explain why you get, in some cases, diurnal tides, some cases mixed tides, and in other places, mostly semi-diurnal tides. Now, this is a little bit of a kind of animation of the bulge moving with the declination of the Earth. So you can see sometimes the moon is on the equator, and other times it's way off the equator. And that has to do with both the moon's orbit, but also with the seasons, because the angle between the moon and the sun can vary dramatically. So here, I'm going to show you what happens, and this is a bit of a weird one. I'm going to see if it works. It's sort of showing you how, with the moon orbiting right around the equator, the forces kind of go in circles. But if I do the other one here, when the moon is north of the equator, you get the forces turning into kind of pretzels. And so the effect of having the moon, kind of lopsided position can have a big effect on the 2 tidal bulges. Oops, okay. So if you were to look at a couple of months worth here, and this is again for the Seattle graph, if you look at the lunar declination, and the declination is just the angle of the moon to the equator, you can see that in Seattle during the month that they were doing this, October 2016, it ranged from about plus or minus 18 degrees. And what you'll notice is that at the peaks and the troughs of the graph here gives you peaks of effect of the moon. And so you can see here that the moon's declination is having a big effect on the, I guess that would be about the 7th of October, but it's having a very small effect on the 15th, 16th of October. And if you then take this graph, and this is the whole year graph, and what I think is kind of cool about these two graphs is the top graph is essentially the observed tides in Seattle for a year. If you were to take the green pattern, the orange pattern, and the yellow pattern that you can see in the bottom graphs, which represent the semi-diurnal pattern, the spring neap pattern, and then the sun declination and the moon declination, if you were to add all those three together, you end up with the pattern that you get up in the top. And so those three factors, the varying position of the moon relative to the sun, which gives us the spring and the neap, the varying distances, which is the ellipticity, and then the varying angle for the sun. And notice that the angle to the sun is greatest in December and June at the solstices, and least in the equinoxes, March and September. But if you were to add those three sets of graphs together, that pretty much explains the overall tidal pattern. So when you're trying to explain the tidal pattern, we have twice-a-day tides that are forced by the sun and moon with this spring neap variation. And that's modulated by the ellipticity of the moon's orbit. Remembering that sometimes the moon's closer, sometimes it's further. And that pattern isn't always in sync. And then you have once-a-day tides, which are forced by the declination of the moon, the angle of the moon. You also have once-a-day tides that are forced by the declination of the sun. So going back here, you can see that you've got kind of these three major factors that are explaining the tide patterns. So the next question, and this is thanks to Norm, is many of you have probably noticed that in the winter, we tend to get mostly high tides during the day, and the low tides are during the night. But in the summer, we tend to get low tides during the day and more high tides during the night. And it's a bit perplexing. But first of all, let's look at the patterns. What I want to do here is, this is a graph of about 45 days worth of tides for Port Renfrew. And this is in winter. And I don't know if you can see on this graph that most of the peaks in this graph happen in the middle of the day. Can you see that most of the big peaks are happening in the yellow spots? The yellow is daytime, the purple is nighttime. But if I switch to summertime, you'll notice that the biggest peaks are in the night. So that's first of all confirming Norm's observation and the fact that, so basically in the winter, we tend to get more daytime high tides. In the summer, we tend to get more daytime low tides. This is another graph produced by a program called JTides. And what it does is, again, it kind of plots you a whole month at a time. And to read this graph, you can see that in winter, the white represents high, the dark represents low. And you can see that in general, in the middle of the graph, around about noon, you get a lot of higher tides. And if I go to summer, you can see that you tend to get a bunch more lower tides. And so looking at that graph, you're kind of looking up from the 12 o'clock, the noon. Notice that it's mostly browns and greens around noon in the summer. If I go back to the winter time, it's mostly whites and blues with a little bit of pale green at noon. And so again, winter time, the high tides are in the day primarily, and in the summertime at night. So the question is, why is that? And I'm going to try and come to that in a minute. I think I've got my slides are out of order here. So the other thing I wanted to mention before I go on is the effect of weather, because in the winter, we tend to get a lot of weather. We're noticing that. And I want to compare the tide levels this last week or the last 2 weeks. So October 24th and 25th, when we had a storm, that was the storm that caused those containers to fall off. And then in October 30th, 31st, we had some really nice weather. So here is the top graph is Victoria Harbour graph, where you can see the red line shows the actual water level and the black line shows the predicted. That was for October 24th, 25th, but take a look at the 30th, 31st. And you see there's a huge difference between the red, which is the actual recorded tide height, and the predicted tide height. And it's a little hard to see on this graph, but it's about almost a meter, almost 60 centimeters of difference, almost 2 feet of difference, 2 feet higher because of the weather. So two things that happen there. The storm winds tend to push water up into the our corner of the Pacific. And then the actual air pressure being lower also causes that. And so that's for Victoria. And then this shows you the same effect for Port Renfrew. And you can see that on October 24th, 25th, the red line and the black line were pretty close together. But on October 30th, 31st, which is the top line, they're pretty close together. But then on the 24th, 25th, they were quite far apart by, again, over half a meter. And if you look here, this is again that Seattle graph, and you'll notice that the black line there in the top graph is sort of the average of all the tides over multiple days. And what that does is it kind of filters out the high-low. But what you might notice looking at the lower graph, which is kind of taking that same black line and putting it on a different scale, is basically from October through March, the water levels tend to be a lot higher with a bunch of peaks, and those peaks coincide with storms. So the weather has a significant effect on tides. And as you can see, going back to, let's say, the recent storms that we had, it can add, 60 plus centimeters or almost 2 feet to the tide height. And okay, and so what would give us essentially the perfect tide storm? Well, you need to have a spring or a neap tide. you want to have the moon at perigee, meaning the moon is closest to the Earth. You want to have the Earth at perihelion, right? So that it's closest to the sun. So everything's at their maximum force. You ideally want to have the moon on the ecliptic, i.e. on the equator. So you've got the same plane. And you add into that a winter storm. And you have what we call a king tide. So I thought I had, okay. I guess I don't have it here, but I'll come back to that. This map here, or this diagram here, is a little animation that shows you kind of how the tide bulges move around the globe at one point. And I'm just going to put that into play. You can kind of see that the brown is the waters of the Earth, obviously not to scale. You can see how the tidal bulge kind of runs up the west coast from California up to Alaska. And so this is essentially an animation of what the tides would look like on the globe there. Okay, and this is a animation of our local tides. And I think what you might notice here is the Salish sea tides are totally out of sync with the offshore tides. Can you see that? That the tides in the Strait of Juan de Fuca, Puget Sound, and Georgia Strait are essentially completely out of sync with what's happening outside. So what I wanted to also address is that there's longer variations of sea level, and the moon is kind of on a wobble relative to the Earth, and that tilt varies over time. And so you can go, sometimes the maximum tilt is 23 degrees, and other times it's a maximum of 28 degrees. And so what that means is that the moon's contribution to diurnal tides can sometimes be bigger at other times of year. And so what I wanted to show you here is Seattle in 2017 and 2025. And in 2017, the lunar declination was near its minimum, and at 2025, it'll be near its maximum. And what I want you to see in the next diagram, where the two sets of tides are plotted, you'll see that overall the pattern is kind of similar, but in 2025, you get a lot more like these the red is the 2025. You'll see that there's a lot more lower low tides and more negative tides. Okay, so but another question that you might want to think about is how fast is sea level changing? And in Victoria, it's rising by about 1 millimeter a year. In some cases, the land is still rising due to glacial rebound, and because of that, the sea level is dropping. And so in Juneau, Alaska, it's dropping by 17 millimeters a year. The sea level is actually decreasing there. Churchill, Manitoba, the same thing. It's dropping by about 9 millimeters every year. But globally, it's rising by about 3.6 millimeters every year. Now, what I want to do now is go back to Norm's question, which was, why do we have this difference between summer and winter? And basically it comes to the tilt of the Earth. So if you think about the seasons, in the summer, the northern hemisphere is tilted towards the sun, and in the winter, the northern hemisphere is tilted away from the sun. And so what that does is it offsets the sun's contribution to the bulge, if that makes sense, in a very different way over those two seasons. And so it causes there to be a greater lopsidedness to the bulge. And that's why you get this difference between summer and winter. So in the summer, you get more low tides by day. In the winter, you get more low tides by night and more high tides by day. And I'm just going to go back to here. So just a few resources. If you want to have a couple of good tide prediction apps, there are a few good ones. One's called Tides and Currents by Flight a Map, and that's for Android. And then there's one called Tide Charts Free. The middle icon on the screen there is an app that's free, and it's available for both Android and iOS for iPhone. And that one is probably my go-to Tides app. If I want to check, yeah, it's the one I check the most on my phone. This one, the middle one, which is Tide Charts Free, doesn't have currents. The other one does have currents, and as does this other app called iTides, which is available for iOS. And if you're on Windows, there's a program called WXTide32 and another one called JTides, and I use both of those to generate some of the images for this talk. And for Mac, JTides is also available. So JTides is available for both of them. And these websites here, I can leave that up on the screen for a minute. Basically, you know, the top 4 links there are different sites that give you, what's the word I'm looking for? Yeah, give you tide predictions that you can zoom into whichever area you want. The 4th one there is where you can download all of the official tide tables from the Hydrographic Service. And you probably all realize that they don't make the books anymore. They only make them available as a PDF. And then the 2 lower links are websites that I think have quite good further information on how tides work. And I think those links are in my document that I shared earlier.
Yep. Mike, can you put that little document icon up again? Because some people either weren't fast enough to get their phone out and take a picture, or
I will do that.
Or if there's a link to it that we can post.
I will, I think what's the easiest way to do that?
Yeah, that's what I was wondering, or we can.
Yeah, I think I can go to here. Is that it?
Yeah, I'm wondering. Yeah.
I can certainly, send you a link to that, and we can either put it in the newsletter or.
Well, that's a good idea.
Actually, what I can do, now that I think about it, is let's just go and see here, just a second. Okay. What I'll do is I'm going to find that link.
I might have it here. Let's see if I can get it posted. I will try. Mm-hmm.
find the link very easily here, but see if I can figure this out.
Okay, someone, I found the link and put it in the chat. Someone
Okay.
can check and see if that works.
So I think that's good.
Mike, I've just emailed you the link as well.
Okay, thanks. So anyway, so it's in the
It's in the chat now, yeah.
there we go. Okay, so let me see here. Okay, so I've got
And Norm has asked a question in the chat too. He said, is a 2-foot tide in Victoria the same as a 2-foot tide in Nanaimo?
so what do you mean by the same? So the
Yeah. Norm, maybe you can elaborate.
Yeah, Mike, when I look at tide tables for different areas, I'll see the range of a tide is maybe from 1 foot to 8 foot for a day. And I go to another area and the tide range is totally different. I'm supposing a 2-foot tide is a 2-foot tide everywhere in Canada because it's all measured relative to the datum. But the fact that it differs from place to place probably reflects the different geographical location of that place.
Yeah, so I mean, the one thing I really didn't talk about that much is how much obviously the topography has, and that's partly explains why Victoria is so weird, is that we're at this intersection of the Juan de Fuca, Puget Sound, and Strait of Georgia, and all of those three bodies of water are reacting differently. And the other thing that kind of complicates the picture is that the tidal waves, as they're called, are a bit like bathtub waves, and they kind of slosh back and forth. And so depending on the size and the shape of the bodies of water, that can cause them to amplify or in some cases cancel out.
Yeah.
And so one of the reasons that the Bay of Fundy has such huge tides is because the Bay of Fundy and the Gulf of Maine basically have this what I call bathtub effect, where the sloshing time is the same time as the tidal forcing by the moon, and so that tends to amplify things. And so the Bay of Fundy is unique, or somewhat unique, because of that, the shape of the two bays. Let me just see here. Okay. Okay. See if there's any more questions there. No, I think yeah. So Norm, I'm kind of sorry I don't have what I would really like is a nice what's the word, nice diagram to show you of how the daytime summer tides and the wintertime summer tides, but it is definitely a real phenomenon. And it is to do with the seasonal tilt of the Earth relative to the sun.
I find that surprising, Mike, because the distance from the Earth to the sun is so huge, the tilt of the Earth is insignificant.
Yeah. Isn't that cool? The sun is very, 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 very big.
I know.
And that's why, the moon, which is, a matter of, 100,000 kilometers away, 350 to 400,000 kilometers, whereas the sun is 150 million kilometers, so it's orders of magnitude further away, but the sun is so huge that its tide generation is literally, almost half of that of the moon.
Yeah. Okay.
So yeah. So the sun's tilt does have a significant effect. And then let's see if I can go back into the one diagram that I had. That I think it's this one. And if you can still see that on the screen, but when you're looking at the sort of the relative effects,
yeah,
you can see that the green, they've, the three different sets of lines there.
mm-hmm.
The green line is the one due to the sun declination, which is basically the seasonal effect.
Mm.
And you can see it's a pretty substantial effect there,
Yeah.
compared to the other ones. And if it's in sync with the other ones, then it, the waves add together, and if they're out of sync, they will subtract.
Yeah.
But the net effect is you've got, the moon declination, the sun declination, and then the orbiting of the moon around the Earth, which gives us the springs and the neaps.
Yeah. Complicated.
It's complicated, but one of the cool things is that we can, predict tides both forward and backwards for centuries, because the movement of the sun and the Earth and the moon are actually quite reliable.
Quite predictable. Yeah. Yeah. Amazing.
And that's why you can go up and into your tide program and predict the tides decades ahead.
Yeah.
And I don't know what people in general are using for their tides predictions, but I typically will go with either a website or an app, just because I don't then have to go and remember to add or subtract daylight savings time.
Yes.
Which is what you have to do with the CHS tides tables.
True. Any other questions for Mike?
Can I ask a question to Mike?
Go for it.
Vic here. I thought I saw on one of your slides that showed the movement of the tides. In the northern hemisphere, the flood tide was north, and I think I saw on the southern hemisphere the flood tide was south. Is that due to the Coriolis effect?
Well, I don't think I had that on any of my my slides. I know that in the what's it called, in the around Vancouver Island, you get north and south flowing tide currents. Because of basically the tide flooding in around the north end of the island before it's reached up.
Yeah.
But I think I think that the tidal bulge basically goes counterclockwise around the Pacific. So both north and it doesn't really relate to the hemispheres.
Hmm. It's on the slide where it showed, you had one there showing the movement of the tides globally. And the southern
Oh,
hemisphere appeared to be going south, like here, see, around Australia. Whereas in the northern hemisphere, they were going up to the north. But maybe that's my misinterpretation of it.
no, I don't know. I think you might be right, but it's yeah, the way I could answer that one would be to I'd have to go and look at the time of high tide in, say, Guayaquil, and then in Callao, Peru, and then Chile, and see how it.
I notice actually in the South America around Cape Horn, they appear to be going north, but around Australia, they appear to be going south. Maybe that's
Yeah.
a little confusing.
I think part of it is just the nature of the animation.
Okay.
And the scale can be, you can see that in a lot of coastal areas, it can get pretty messy.
Right.
But
yeah,